Okay, so just a recap uh, from the last set of topics. So you would have met the idea of an exterior point. So just recalling this stuff now. So a point X not belonging to the set A is said to be an exterior point of A if there exists some radius such that there's a neighborhood around that point inside of A complement. So you could think of if it looks like the definition for an exterior point, if it looks like that definition is similar to that of an interior point, you will be exactly correct because an exterior point is just an interior point, but not of the set A. It's an interior point of A complement. So if you want to get the definition for an exterior point, just apply the definition of an interior point, but you are applying it to the set A complement. Okay? That is X is an exterior point of A if X is an interior point of A complement. Okay, so it's the same definition, but you do not apply it to the set A, you apply it to the set A complement. And just like the interior of a set, we could group or we could take the set of all exterior points of A, and that is called the exterior of A. Now, what is a boundary point? So a point um, X belong well, a real number is said to be a boundary point or a frontier point of a set A if for every radius the neighborhood around that point contains a point of A as well as a point of A complement. So the points of the real number or the points of any set that is neither an interior or an exterior point will be a boundary point. Boundary point means every single neighborhood around that point has points of the set A as well as points of A complement around it. So you are on the border, you're on the boundary of these two sets, A and A complement. And just like before, we could take the set of all these boundary points, and this is called the boundary, or sometimes the frontier of A, and it's denoted commonly by BD of A, or you see usually this partial derivative symbol of A. So this is not differentiation. This is just the symbol they use. So you have exterior boundary. And this was the picture uh, from the last video that you should have in mind. So you have some set here. The interior, you should view that as the inside. The exterior, you should view that as like the outside. And of course, the boundary would be this red dotted line. So that gives the following result. For any set A, the interior of it union the exterior union the boundary gives the entire real numbers. In other words, what this is saying is that if I tell you I have some set A of the real numbers, um, and I give you any real number X, then that real number is going to be in at least one of these sets. That real number will either be an interior point of this set, an exterior point of this set, or a boundary point of this set, right? So it's sort of like you're breaking up the real numbers with respect to this set. Now, the second one is very useful. It's saying that the exterior intersect. Now remember what A prime was. A prime is the set of all limit points, sometimes called the derived set of A. So all the limit points live in here. This one is saying that if you are an exterior point, then you cannot be a limit point. Or if you are a limit point, you cannot be in the exterior. So these two sets are disjoint. The proof of this first one follows directly from the definition of the interior, exterior, and boundary. I put here, try to draw a picture. So that picture was the picture we just saw previously. Okay, so this first one is pretty straightforward. Just look at the definition of interior, exterior, and boundary side by side, and you will see that if you have a point, if you have a real number, it has to be in one of these. Now, for the second one, I want to prove that the exterior intersection, the set of limit points, this derived set, is the empty set. So we're going to try to do this using a proof by contradiction. So I assume that this intersection is non-empty, and now I need to figure out how to get a contradiction. Okay, if the intersection is not empty, then there is an element x belonging to that intersection. So this element x is an exterior point and it is also a limit point of E. So now we are going to apply the definition of an exterior point. Since x is an exterior point of A, so by definition, there exists a neighborhood such that there exists a radius such that that neighborhood is entirely contained within A complement. That is the definition of an exterior point. And notice that if the neighborhood is entirely within A complement, if I remove a single point, if I remove a point of this neighborhood, then that new set is also in A complement. Okay, if you have two sets, X subset of Y, and you remove a point of X, then that set is still inside of Y. So by that logic, if I remove now the center of this neighborhood, which we know it's called a deleted neighborhood, and we denote it by N with a little star, then the deleted neighborhood is also in A complement. Okay, so if the deleted neighborhood is entirely within A complement, then this deleted neighborhood intersection A, not A complement. If you intersect this deleted neighborhood with A, that is the empty set, right? So the deleted neighborhood now intersection A is the empty set. That means we have found a radius such that there is a deleted neighborhood around that point that has no points of A, which means that X cannot be a limit point of A. So you will have to see what is the definition of this limit point. Okay, and of course that is a contradiction because we assume that X was an exterior point and a limit point. So that leads to a contradiction. Therefore, the exterior intersection, the derived set, is the empty set. And these two results will be very useful when we need to figure out, given a set, if I want to figure out what is the interior, what is the exterior, what is the boundary, what is the derived set, these two results will come in handy. So for example, the open interval AB. Okay, I want to figure out what is the interior, exterior, boundary, the limit points of this set. So let's figure out what is the interior. Now we know that all open intervals are open sets. So A is an open set. If you are an open set, then the interior is equal to that set. Okay, so therefore the interior of A is simply the set A. So that is easy enough. What is the exterior of this set? Now the exterior is the same as the interior of A complement. So to get the exterior, what we're going to do is we're going to write down A complement, and we're going to look at that set, A complement, and try to figure out what is the interior of that new set. So this is A complement, right? If A is open interval A to B, this is all points between A and B, then A complement is all points less than A, which is this guy, together with all points bigger than B, which is this part. Okay, so this is the set A complement. Now look at this set and try to figure out what is the interior of this set, right? What is the, since we know that the interior is the largest open set I could fit in here, and we know that the open sets are all built from open intervals, this you could think of as asking yourself the question, what is the largest collection of open intervals you could squeeze inside of this set, right? So if X belongs to this set, then either X belongs to minus infinity to A union B to infinity, or X is equal to A, or X is equal to B. Okay, so we have three cases if we belong to this set. So the first case, if X belongs to minus infinity to A union B to infinity, remember that these are open intervals. So these are open sets. And the union of two open sets is an open set. So this set and its interior are the same. That means X belongs to this interior. Okay. And the interior of this set is, of course, contained in the interior of the big set, which is A complement. And we know that the interior of A complement is the same as the exterior of A. In other words, every single point X belonging to minus infinity to A union B to infinity, every single point in this set belongs to the exterior of A. Okay, so since open intervals are open and the union of two open intervals is open. So we have a lot of points right away for the exterior. Now we just need to check, are the points X equal A or X equal B also exterior points? Or are these points interior points of A complement? And we know that, for example, if X is equal to A, then for any radius, epsilon you take, if you try to put a neighborhood around that point A, this neighborhood is not going to be a subset of A complement. Okay, so if you look at this set here, this set A complement, and you look at A and you look at B, we already know from our previous study of the open sets that this point A and this point B are not interior points of this set. Okay, so if you are not an interior point of A complement, then you do not belong to the exterior. Remember that the interior of A complement is the same as the exterior of A. Okay, so A does not belong to the exterior. And in a similar way for B, if X belongs to B, same thing. For every radius you choose, if you put a neighborhood around B of that radius, this neighborhood is not going to be within A complement. So A and B are not exterior points. So if we collect all these results together, what is the exterior? The only points we found in the exterior were points from minus infinity to A union B to infinity. Okay, hence the exterior of A is this set. And if we go all the way back and we look at what was A complement, right? So forget this is A complement, just look at this set and ask yourself, what is the largest open set I could fit in here? And the open sets are built from open intervals. So what is the largest collection of open intervals you could squeeze in that set? Well, you would say that the largest open intervals you could fit in here would be open interval minus infinity to A open, union open B to infinity, right? That's the largest open set you could fit in there. And that is exactly what the exterior was, right? The exterior is the interior of a complement. So it gives you a good idea as to what you should expect the exterior to be. Of course, you then need to go and verify each individual point, just like you see in this example. Okay, so we got the interior, we got the exterior. Now, to get the last guy, the boundary, um, let me go back to this result. So this result that we just spoke about, it's basically telling us um, another way to find one of these sets. In other words, if you know any two of these sets on the left-hand side, so the left-hand side, you see you have the union of three sets. If you know any two of them, you could figure out the third one, right? How could you figure out the third one? Well, if the union of all these three has to be all of the real numbers, and you know any two of them, then you just figure out what else are you missing in the real numbers, and that will be the missing set. Okay, so in this example, we know the interior and we found the exterior. So the boundary is just the real numbers, and I'm going to remove from that. So this is not subtract, this is set difference. This means take the real numbers and remove from it these sets. So we're going to remove from it the interior and the exterior, and whatever is left has to be the boundary, right? So the interior union the exterior, and if you look at what is the real numbers and you remove all those points, then they are just 2 points, A and B. Okay, so A and B are boundary points of A. Now, the derived set, or the set of all limit points, so we would have shown previously that the interior, when we are in the real numbers, the interior is always, every interior point is a limit point. So in the real numbers, the interior of a set is always a subset of its derived set. Okay. And we also just showed in that proof we did by contradiction that the exterior intersection, the derived set is empty. So what these two things are telling me is that if you are an interior point, then right away you are a limit point. So all the interior points are limit points. The question is, where else could these limit points be hiding? Could the limit points be hiding in the exterior? The second result is saying no. The limit points cannot be in the exterior. So all the interior points are limit points. No exterior points are limit points. So what other set is left? The interior, the exterior. The only other set is the boundary. So these two results, when you combine them, they tell you that the only other place where possible limit points could be hiding is on the boundary. So the boundary is what you need to check. Okay? So hence we consider the boundary points A and B, right? So we found the boundary points up here. So the proof of one of these is the same as the other. So we just need to essentially do one of them. So I want to argue that these are indeed limit points. Oh, sorry, boundary points. These are indeed boundary points. Boundary points again mean if you take any neighborhood around, let's say A, any neighborhood, no matter how big or how small that radius is, there will always be points of A and A complement in that neighborhood, right? And again, if you're able to draw a picture of the set, in this case, the set is just open interval AB, so that's a very easy picture to draw. Then you could easily see from the picture, or you should be able to get an idea what the boundary points would be. The boundary points would be like the points on the end of the set. Of course, again, the picture is not a proof, right? You need to write down the proof properly. Okay, so how to verify that these points A and B are indeed limit points? Oh, sorry. Yeah, limit points. Okay, so for every, so I need to show, for every radius, the deleted neighborhood around the point A, so A is a boundary point, intersection A. So this deleted neighborhood, you could write this as A minus infinity up to A. Then you jump over the center. So you go union A to A plus epsilon. So this part in the square bracket, that is just the deleted neighborhood. And then you intersect this guy with the set A. The set A was open interval AB. Okay, so when you do this intersection, you get this set. Notice that this set here is not empty. In other words, for every radius you could find, the deleted neighborhood around this particular point A, intersection the set A is always non-empty. In other words, well, the same thing for B. So for B, same argument. In other words, A and B are limit points of A. Okay, so totally, what is the derived set? The derived set is A and B union the interior. Remember, in the real numbers, all these interior points are limit points. Right? So therefore, the derived set or the set of all limit points is equal to the interior union the boundary points. The interior we found was open interval AB. Union, the boundary points we found were A comma B. So this you get closed interval AB. Right? So that is the derived set. So what if we look at the rationals or the irrational numbers now? What's the interior? What is the exterior? What are the boundary points of these guys? So we already know that the interior of the rationals is the empty set. So the exterior of the rationals is the interior of its complement. And of course, the complement of the rational numbers are the irrationals. But we already know that the interior of the irrational numbers is the empty set. So the rational numbers has no interior and it has no exterior. Now remember that if you are a real number, you are either in the interior of a set or the exterior or the boundary. But the interior is the empty set. The exterior is the empty set. Therefore, the boundary of the rational numbers must be all of the real numbers. Okay, so let me go all the way back and show you what we're using. We're using this result. So substitute for the set E, the rational numbers, Q. So the interior of Q union the exterior of Q union the boundary of Q equal R. This interior is the empty set for the rationals. The exterior for the rationals is the empty set. So empty set union empty set is empty set. Empty set union the boundary. So this is the boundary of the rational numbers. Therefore, the boundary of Q equals all of the real numbers. So this is the result they are using. Yeah. So that's how they got this result. The boundary of Q is all of the real numbers. In other words, if you take any rational number, sorry, if you take any real number and you put any neighborhood around it, you will always find a rational number and an irrational number. Of course, we already knew that. That's the dense property of the rationals and irrationals in R. So this is another way of saying that. Right? So if x is a real number, then for any radius epsilon, there is a rational number between x and x plus epsilon. Right? So we know that. That is, there exists a rational number R such that this rational number is between x and x plus epsilon. So it's in this open interval. And of course, this open interval is contained in this deleted neighborhood, right? Because the deleted neighborhood is this guy, but union x minus epsilon up to x. Okay, so if I then take this deleted neighborhood and I intersect it with Q, it's going to be non-empty. Why is it going to be non-empty? Because the deleted neighborhood contains R, and R is a rational number. So the deleted neighborhood contains at least one of these guys. In fact, it will contain infinitely many. But it just needs to contain one to be non-empty. Okay, so therefore, X is a limit point of Q. Okay, hence the limit points of Q are also the real numbers. So again, what this is saying is, if you take any real number, and you look at any neighborhood around that real number, so the real number could be rational, irrational, doesn't matter. If you take this result is saying if you take any real number and you put any neighborhood around it, no matter how big or how small, you will always find a rational number. Okay, so in other words, the set of limit points of Q is the real numbers. And it's the same sort of proof structure, same results you get if you replace Q by Q complement. So it's the same result for the irrational numbers, right? So what I'm saying is that the boundary of Q complement is R. The limit points of Q complement is R, right? And how would you prove that? It's the same proof, right? Just anywhere you see the word rational number or Q, you substitute irrational number or Q complement, and it's the same proof. So try to sit and write down that proof. Okay, so what about the integers? Well, we know that from studying open sets that the interior of the integers is empty. Okay, and the exterior of the integers, well, that's just the interior of the integer complement. And we already know that Z complement is an open set. So the interior of an open set is itself. That's why the interior of Z complement is Z complement. Okay, so the interior is empty, the exterior is Z complement, so whatever is left over must be the boundary. So what is the empty set? Union Z complement. Well, that's just Z complement. Okay, and if you take all of the real numbers and you remove from them Z complement, so take all the real numbers and remove everything that is not an integer. What are you left with? You're left with the integers. Okay, if you take all the real numbers and you remove from it Z complement, you have Z. So in other words, the boundary of Z is itself. Okay, so every, and if you think of it, if you think of an integer or the integer, this should make some sense because if you are an integer, let's say you're 0, and you put any neighborhood, any open interval around 0, you will find in that neighborhood an integer, 0, and points that are not integers. For example, the fractions, so a half, a third, a quarter, and so on. So that is why the boundary of Z is Z. Now, what about the limit points? So for every real number, we could find a radius such that the the deleted neighborhood around that number of that radius intersection Z is the empty set, right? And I put this, you should verify this. So to say why this is true, draw out, try to draw a couple the real number line and put a couple integers there. And then pick a random point on that line, X. Then put a neighborhood around that point that does not intersect any integer. You will see that it's very easy to always do that. Okay. So in other words, what this is saying is that the integers have no limit points. Right? So X is not the limit point of Z. In other words, the limit points of Z, which is Z prime, is the empty set. So all of these results, um, it is very difficult to grasp it when you now see it. These results, you need to sit down and you need to draw some pictures or write it out and try to go through it step by step very slowly and try to understand why these things are true. Okay, so don't try to just learn off and cram off that the interior of the integer is empty, the exterior of the integers complement. Don't try to cram off those stuff. Because if you get a set that is different from the ones that you've seen before, then what are you going to do? Right? So you need to sit down, try to draw a picture if possible, and see why it is these results are true. Okay, and then once you could see why it's true from the picture, you then need to try to sit and write down what these statements should be mathematically. Because in the exam, on the assignments, and so on, it is these results or these statements that you need to reproduce, okay, for a given set. All right, so another example that I'll leave for you all to look at. So all of the working for this one, the interior, exterior, boundary, derived set is in the course notes, but I'll discuss it with you. So this set A, this set contains these points. One points of the form 1 over n, where n is a natural number. So in other words, the set A contains 1, a half, a third, a quarter, a fifth, and so on. Okay. So notice that there are no irrational numbers in this set, right? They're all rational numbers, and you have a sort of diagram over here. So you see from the diagram that all of these points, you see they are clustering closer and closer to 0. Notice that 0 is not in A. 0 is not in A because there's no natural number you can give me such that 1 over n equals 0. So 0 is not in the set. However, the interior of this set is the empty set. This set has no interior. The exterior of this set, now you need to sit down and again think about why is this set the exterior. Okay, so try to construct a complement and ask yourself, what is the interior of a complement? That is this guy. The boundary points of A is the set A together with 0. And the set of all limit points, it turns out this set only has one limit point, and that is 0. And notice 0 does not belong to A. Okay, so the limit points does not have to belong to the set. Okay, so the proof here I put self-reading. So page 32 in the course notes. So sit, and try to write it down, write through it, and see if you understand. Okay, so now we're going to move on to another set, something that is called the closure. So for any subset A of the real numbers, the closure of A, denoted by A bar, is defined by the set union its limit points. So to get the closure of a set, you take the set and you add to it its limit points. Now, the reason, so you should think of the closure when we studied the open set, we had something called the interior of that set. Now, the closure is the analog of the interior, but for the closed sets. So for open sets, we look at the interior. That's the main guy. For closed sets, we look at this guy, the closure. That's the main guy. So what are some properties of the closure? So for any set A, the following statements are equivalent. A set A is closed if and only if its complement is open, right? So we know that that's from the definition. Or another way of saying a set is closed if the limit points of A is contained in A. So usually, or in a lot of books on these things, they may define a set is closed if it contains all its limit points. So this is how you should think of what a closed set is. A set is closed, so anytime you're dealing with closed sets, the way you should interpret that is it contains all its limit points. Notice if a set contains all its limit points, if A prime is a subset of A, then if you look at the definition of the closure, right? And if A prime is already inside of A, then when you do this union, what will you get? You will get A, right? Because if A prime is already in A, then when you union it, you'll get A. So that gives the last result. A set is closed if and only if it is equal to its closure. Okay? So the proof is omitted, but I put here, you could still try it yourself as a practice. Now, you could look back at the theorem so there's a similar theorem when we studied the open sets, but it dealt with the interior, right? And I told you all that the interior of a set, another way to look at it is it's the largest open set you could find inside of it. So the interior is the largest open set you could find inside of that set. The closure is the smallest closed set contained in that set. Okay, so I draw a drawing. Let's see if I can give you a drawing of this. Okay, so what am I drawing? Right, so this is some set A, right? And we know a couple of things. A is open if and only if A is equal to its interior. Now we know that A is closed if and only if A is equal to its closure. So you see the closure and the interior, they are two analogs of these different concepts, open and closed. So when we talk about the open sets, we look at the interior. When we are dealing with closed sets, we look at the closure. Yeah, so I told you all that the interior of a set, interior, okay, so of course you know A with the little circle is interior. Okay, that's another way to write it. So the interior of a set A, okay, the interior of A, also you can write as A with a little circle, is the largest open set inside of A. Okay, it's the largest open set containing A. That is why, if A is open, it is equal to its interior. Now the closure is out here. The closure is A union something. It's A union. Remember the closure is A union its derived set. So the closure should be bigger than A. That's why we draw it on the outside. So this is the closure. It's A together with its limit points. So the closure, this is the smallest closed set, smallest closed set containing A. Okay. So this is how you should, view these sets. You have the set A, that inside of it, the largest open set is the interior. Outside of it, the smallest closed set you could find that has A is its closure. Okay. And there are proofs of these things, by the way. To prove that the interior is the largest open set inside of A, what you have to do is show that the interior is the union of all open sets in A. To show that the closure is the smallest closed set contained in A. In order to prove that, you will have to show that the closure is equal to the intersection of all closed sets contained in A. Right? So, of course, um, when dealing with open sets, the union of any amount of open sets is an open set. And when you're dealing with closed sets, the intersection of any number of closed sets is a closed set. Yeah, so we also have these results on how the derived set and also the closure distributes over union and intersection. So it's very similar to the interior. So look back in your notes and you'll see there's a similar theorem that dealt with the interior and it looks just like this. Okay, so A union B, if you take the set of all limit points, that's equal to A prime union B prime. However, if you're dealing with intersection, you don't get equality over here. The best you could get is a subset. So right away, when you don't see an equal sign, that means there are many counterexamples you could come up with where the left-hand side is not equal to the right-hand side. So try to come up with two sets, A and B, where this left-hand side is not equal to the right-hand side. Now, from these two results, you could then prove that the closure of A union B is equal to the closure of A union the closure of B. Okay, so that follows straight from this first guy. And the intersection, if you do the closure of A intersect B, you can prove that that is a subset of the closure of A intersection closure of B. So that follows from this second result. And if A is a subset of B, then you could take derived sets and you could take closures on both sides of the subset and you keep the subset. Okay, so then if A is subset of B, then A prime is subset of B prime and closure A subset closure B. Okay, and the proof is left as an exercise for you to figure out. Of course, if you get stuck, all of these are well-known results that you could find very easily if you just Google this, or you could find this. These are standard results in any textbook. You will find this stuff. Okay, but you should sit and you should try to prove it, because then only by sitting and trying to prove these results, um, will it tell you that you really understand, for example, what are these limit points, what is a closure, and so on, right? And these results, it's not anything long and complicated. Most of these results are 2 to 3 lines long, and they follow straight from the definition of limit point, straight from the definition of closure, straight from the definition of union and intersection. So other than those things, you don't need to be pulling some result out of the blue to try to come up with these things. Okay, so you should try this stuff. Yeah, so I said try to find an example where this one is not a subset of this. So I'm making reference with respect to the second one, right? You see the second one, you only get subset, which means that there's an example where A prime intersection B prime is not a subset of A intersection B all prime. Okay, so the connected sets. Okay, so that's where I wanted to reach today. So we will stop there.